Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, everyone. Welcome to the 39th Symposium on a Friday the 13th. And so far, everything's gone smoothly. Most of you probably know the drill, but drinks are through this door. There's also coffee out there, restrooms through the back door, and then in this direction. I hope if you're parking in the garage, you registered your car with a receptionist. If not, you might want to dash out and quickly do that. And I think we've got two really interesting talks today. And Faye is actually going to introduce our first speaker, Dan Garrett.
Okay, it's my pleasure to introduce Dan Garrett as the speaker from our UW side. He received his PhD from UT Austin last year, and he's a postdoc at CSE department at UW, and he's working with Luke Zettelman. So I'll turn to Dan.
Hi. All right, so I'm going to be talking about a project that I've been working on for about 2 years now. Sort of a side project to what I've been doing, but it's really interesting and fun, so I thought it'd be fun to share. So this is work that I've been doing with Hannah Albert Abrams, who's a student at UT. And the project was sort of originated by Dan Klein, Taylor Kirkpatrick, and Greg Durrett at Berkeley, and we've worked with them as well. Okay, so the talk here is about document transcription, so transcribing historical documents. So just so we're all on the same page, this is a historical document, and our goal is to digitize it into text. We've specifically been looking at a collection of texts from the Primeros Libros project. So this is books that were printed before 1600 in Mexico on the first printing presses brought over from Spain. There's a website, primeroslibros.org, where these you can view these books. They're all high quality scans. A lot of these books are from private collections, so it's really nice to be able to have access to them. So we're going to talk about a couple of things here. So I'm going to talk about what the challenges are with this problem, how we model it, and our technical contributions. And I'm going to talk about something I think is really interesting, which is the implications for humanities, in particular digital humanities. All right, so we'll start with the challenges. Okay, so one of the big deals with historical documents is dealing with the visual noise. So this is not stuff that's printed on a laser jet. So these are books that were printed by lining up little pieces of metal type and then slapping ink on there and pressing them down. And so you get places where the ink is splotchy. You get places where there's not enough ink and it's hard to read the letters. You also get places where the alignment is off because they're lining up these letters, and sometimes the words are kind of smushed together, and so you end up with all these interesting challenges. The fonts that they used are also unknown to us, so they're not using Helvetica. So these are fonts from my computer, but none of them exactly match here. So we've got to learn unsupervised what the font actually looks like. So the books we're looking at, they use not even a standardized font within the small group that we're looking at. So you can see all sorts of things. So the older ones use this black letter font, and none of them really look the same. The other challenge in recognizing the letters is that they look different all the time. So knowing what an A looks like, it could look like that or whatever. All right, so we're building off the system Ocular, which was the paper that Taylor, Greg, and Dan originally gave us. So I'm going to give a little bit of background on that before moving on to our stuff. So Ocular works as a generative model. It has three parts. So first there's a language model, then it typesets, and then it renders the letters. So the language model part is going to model a sequence of characters. And then each character is going to produce a bounding box and space in between, and a vertical offset, because some letters are going to be higher than others, and an amount of inking. And then based on that, it's going to produce a set of pixels that's going to represent the letter. Our focus is going to be on the language model aspect, so we're going to reuse the other parts. Okay, so one of the challenges with these books that were printed in Mexico is that they are mostly multilingual. Even the ones that look monolingual still have multilingual aspects to them. And not only that, but they switch readily between these languages. So here's a page from a book called The Advertencias. It was printed in 1600. And so it's got Spanish on it, it's got Latin on it, it's got Nahuatl on it, and they're just all jumbled up. So there's no chance for us to segment into pages that are specific languages. We've got to handle this jointly in a single model. Ocular's original language model was really straightforward. It uses a smooth character 6-gram model. They estimate the parameters in the usual way, so they have a bunch of text. They count up the n-grams. And so when we first got the model first got the software from Taylor, we were really excited and we ran it through the system. And of course, the language model that he used was in English, and so the transcription was really bad. And you got things like English words. Okay, that's to be expected. So we did the natural thing, which was to take corpora from the 3 languages that were relevant to us, smash them together, do the same estimation. And what we get is a really bad transcription, and with exhibiting what we're calling the multilingual blur. So the statistics are getting all confused, and it's not doing a very good job. So in order to handle this, we developed a code switching model in which we develop 3 separate models, 3 separate n-gram models, and the characters here are annotated with the particular language. And the key here is that we allow switching between the languages at the character level. And this gets such a much better transcription, and it also gives us a labeling of what language each character is in. So some more technical notes. We want to learn the transitions between the languages in an unsupervised way, along with the standard training procedure. And there's this key of having a hyperparameter to prefer not switching. So when we didn't have that, it switched too readily because it's trying to figure out what the letters look like, and it picks a word. And if we tell it that by default words that are next to each other are the same language, then it does a lot better by trying to force those to stay the same. So here's this page from the Advertencias, and so we're looking at a string of characters here. And so we're going to have a set of potential characters for each language, and so these are language specific because, for instance, Spanish has accents and Nahuatl doesn't. And so we're going to come up with a bunch of states, and so when we do our decoding, either for EM or for the Turby thing, we're going to have a lattice that goes for each character. Now, this is a simplification because the system is actually doing joint segmentation as well as figuring out what the letters are. So keep that in mind. So the goal here is to find a path through the lattice. And so here it's choosing to call this Nahuatl. And then when we hit a space, we allow changing between languages. We don't allow changing between languages within a word because obvious. So this is a Spanish word, and of course we hit another space, but we're going to stick with Spanish. The other challenge that's really interesting here is this concept of orthographic variability. So spelling at the time, really inconsistent. So here they spelled a word like dice as dize. So there's a lot of these letter alternations. So there's U and V and B and V and some others. And they also didn't use accents the way that standard accents are now standardized in Spanish, but before they just left them out all the time. The other really interesting one is this printing shorthand that they did. So the paper that they printed on was really expensive. It was brought over from Spain. In order to conserve paper, what they did was, if a line almost fit, they would leave out some letters to make it fit in there. And there are patterns to this, but the patterns vary across who the printer was. So these variabilities are region-specific, time-specific, author, printer, document-specific. And so if we were to try and produce language model training data that was representative of each of these things, we would be stuck. Trying to figure out what all these possible variations are is a non-starter for us. The other interesting thing is that the indigenous languages, so Nahuatl, before the Spanish arrived, had a pictorial writing system, which does not lend itself to printing on a printing press. So they developed a Latinized version, and it was being still developed at the time, obviously. So when we need language model training data, we go to Project Gutenberg. They've got text in lots of languages, and that's easy for us. However, they use modern spellings. They're not going to have the shorthands in there as somebody's typing it out because it would be really hard for us to read. As an example here, just for the challenges, so this is one page of one book. We see the word mentere, it's spelled two different ways. So one, it leaves out the N and puts a tilde over the E to mark that. The other one, it doesn't. There's a field in the humanities, scholarly editing, and they've thought a lot about what it means to produce correct output from a system like this. And so there's sort of two choices that we boil down to. There's a literal transcription, which they refer to as diplomatic, and there's a normalized transcription, which might be modern, it might be something else. And so in order to figure out what we should do, we asked people, we asked book historians, we asked scholars of Nawad, what they would prefer, and half of them told us one and half of them told us the other, because some want to study the way that people wrote and some want to be able to search for a particular word and see all the places it appears without having to think of every possible spelling variation. And so modeling these things is really important. So if you don't do any orthographic variation handling, this word, mentere, gets rendered as merita, which is also a Spanish word. It's just not this Spanish word. And the reason it does that, obviously, is because it doesn't know that there's an N that's been left off there. And the R and the T really look similar. And so it's trying to fit that to a word it knows. So when we model this, we want to make sure that we understand that N is being left out. So our approach is to induce a probabilistic mapping between the normalized writing and the orthography of the document. So we'll see what that looks like. So it's a generative model. Obviously, we are trying to figure out where the pixels came from. So we're going to have a sequence of states. Now, our states are actually character level, but I'm just glossing over that for now. So we might call this, it should actually be Spanish, I'm sorry. And so we generate the word persona, and so this is a standard spelling because that's what we sort of expect to see. And the letters in this are going to produce, they're going to generate the letters that are actually going to be rendered. So the S here is going to get rendered as a long S. The O is going to be rendered as an O with a tilde because the N is being left out. And so for each of those letters to be rendered, we're going to produce a bounding box, we're going to produce a vertical offset, we're going to produce a amount of ink, and then we're going to render the pixels. So what's really interesting here is in our model, we actually end up with two transcriptions, not the one that we would normally have. So we end up with a literal transcription and we end up with a normalized transcription. We also end up with a tag on the language of the word. So having this joint thing is really cool because the standard way to do this is with a pipeline. So typically you run an OCR tool, you get a literal transcription, then you run a post-processing rule-based system to normalize it. These rule banks are enormous and they have to be produced by hand. And so it just doesn't work very well because as we've seen, if you don't handle the orthographic variation, the literal transcription is really terrible. And so trying to normalize from that is just not going to work very well. When we learn the parameters of the model, we use expectation maximization. I'm not going to say more about that. So in order to know how well we're doing, we ran some experiments. So we evaluated our system on 7 books from the Primaris Libros project from different time periods, different printers, different readability in terms of quality, different languages. We wanted to have a baseline so that we could see if there's an easier way to do this. And so our baseline was to take the modern Spanish that we got from Project Gutenberg, have a list of replacement rules, because we want our language model to look like the data in the book. And so we basically transform the modern Spanish into something that looks like what the document has. So this is kind of interesting because So we do better on the normalized transcription. So if we don't do any orthographic variation handling, basically we're just kind of targeting a normalized transcription because we are trying to, basically we're trying to model the word as the language model tells us. If we do this rewriting, then we're changing the normalized version to the version that we expect to be in the document, and so we're sort of targeting the diplomatic version. But our model actually does both. And so we are able to dramatically improve the normalized version without losing too much on the diplomatic side. To see some outputs, you can see that we capture lots of things. So we get this qual to qual with a C, so they used to spell it with a Q. In the word está, they use the long S, which if you don't handle the orthography, it gets confused about what that is. it captures that QUE is sometimes written as Q tilde, that accents get dropped, and sometimes they would double letters, so this happens frequently. Another cool thing that we didn't really think about, but totally happened, was that we caught typos. So this one here, they wrote an R instead of what should have been an E. Without the handling, it tries to fit that, and it comes up with an I. But in our version, we recognize that it's really an R and that it should be an E, and so our output contains that. There's some stuff that we just don't do very well. So Jesus Cristo, where Cristo is written as XP tilde O. So that's written that way because it comes from Chi Rho, which is a Greek way of writing Christ. And so our system has just no ability to do that because we don't know how to learn a mapping from Cristo to XPO. Another kind of interesting thing is that because the Nahuatl orthography wasn't standardized at the time, they didn't use a lot of spaces in these documents. And so our language model training data has spaces. The original document has these really long words. And the evaluation is funny, right? Because we do pretty well on the character evaluation, but not the word evaluation because it's unclear what a word is. Now I want to talk about the sort of broader implications of this in terms of humanities, in particular digital humanities. So as we were doing this project, we wanted to constantly be aware of our goal here. Our goal is not to produce transcriptions. Our goal is to produce interesting data that people can use for further work. The transcriptions by themselves are just a means to that end. And so the dual joint transcription thing was really exciting, and particular for the indigenous languages. So this field of scholarly editing is concerned with how to prepare texts for publication, and so trying to figure out how we can take this indigenous writing and turn it into something that we should be publishing is a good question. So for these Nahuatl texts, the original people who worked on these, who developed these Latinized scripts 500 years ago, referred to the Nahuatl language as barbaric and described it as being deficient in certain sounds. So this is a really interesting concept. They viewed Latin as being the perfect language, handed down by God or whatever, and they viewed all other languages as deficient forms of it. So Spanish was missing certain sounds, and Nahuatl was missing certain sounds. Now, of course, we know that Nahuatl has sounds that Latin doesn't have, and the monks who were doing this probably didn't even notice that or care. So you get this aspect where the colonialization of this language is sort of wiping out important aspects of what that language looks like. And so when people want to write things now, when they want to publish things in modern orthographies, they're developing new orthographies that decolonialize the text. And so they're adding things like tonal markings that should have been there originally and weren't. And these orthographies are now being produced with the help of native Nahuatl speakers. Another great thing about the fact that this is unsupervised is it allows us to target any normalized form. So the orthographies, as I just mentioned, are changing. There's a book that was just published with a new form of orthography. And so our system is able to, we just take more training data of that form, and it will produce transcriptions in the orthography that we want. And so this is important because the original orthographies are sort of in this colonial context, and we want to produce things that are what we would say as actively anti-colonial. And the great thing about this dual transcription aspect is that we are still preserving the original orthography. So there are historical and societal implications to the way that people wrote things, and we don't want to lose that. We want to keep that because that's part of the historical record. So we want to produce transcriptions that are true to the language, but also capture the historical implications. Another nice thing is that we get more output than if we just did the transcription by itself. So we are producing language taggings, right, that are not sort of in the text, right? It's a latent aspect. And there's metadata associated with all of these books, on the website or whatever, and the metadata is often wrong. So, a book might say it's written in Nahuatl and have huge Spanish sections because if somebody was looking at the book, maybe they didn't notice that. But our system can find that and actually quantify how much of each language, and because it's word level tagged, you can study things like the context in which each of these languages were used. This would be totally impossible to do by hand because you're not going to read through thousands of books and with thousands of pages and try to find all this information. The other thing it outputs is because we have this probabilistic mapping between orthographies, we can actually quantify the ways that people wrote. So we can see here a bunch of major replacements in a Spanish book. And so this is really interesting because it allows us to ask questions. And so one of the cool things is because these orthographies are specific to regions and printers and different things, we can use this information to try and ask, for instance, who printed a particular book. This is something that people in the humanities have done, people in the digital humanities. So trying to find out who typeset particular Shakespeare texts is a project that someone's done. It's also related to this other interesting thing of how scribes, scribes who wrote things by hand, are said to have reinterpreted text. And so trying to figure out what that means in our context, how the orthographic changes what they say about the ways that people chose to print things. So to conclude, we started with scans of historical books, and we produce 2 transcriptions that are language tagged and have the orthography, the original orthography in the text, and a normalized form of the orthography. And so we want to take into account these multilingual aspects, the fact that these orthographies change in order to not only improve the state of the art of OCR, but to also produce data and produce tools that can be used to open up vast resources for people to study these interesting questions further. And if you're interested in reading the more technical aspects or trying the software out, you can find links to these things on my website, and the code is all up on GitHub. Thank you. Yeah.
So you said that one cool aspect of this is that you can detect languages in the text that almost impossible to do manually. But your training data is language models from specific languages. So how do you decide which language models to use?
So you could do 2 things. You could throw language models in for all the languages that you expect. But really, what I'm talking about is that it would be impossible for you to go through and quantify these things. To read thousands of pages just to find out where certain languages were used is sort of a more easy question. But definitely, if you threw in language models for Nahuatl and Zapotec and Mixtec, you would hopefully be able to find those things, because there's nothing that says that every language has to appear in every document. Yeah.
You kind of went through it really quickly, but when you talked about finding the transitions between languages, was that just an EM process?
Yeah. So we count up the places where it appears, and we do a hard EM update on that.
I was wondering if there was any interesting looking into where that happens, or
no. So we thought about that. It's pretty darn good at finding those language transitions, and so we thought about things like, maybe we should look for word cues that tell us when you're going to change, and we haven't looked into it because it doesn't seem terribly necessary. There are some kind of interesting ones. One of the books that we were looking at is a book about Nahuatl grammar. And so it has sort of Nahuatl words thrown in, or Nahuatl, there's a place where it talks about Nahuatl prefixes. So it kind of throws these in amidst Spanish text, and it's not good at finding those because they're just too small and too ambiguous to capture. And so it just tries to transcribe them as some weird Spanish thing. Yeah.
So I don't know what the practice is like in the digital humanities, but is there room for a feedback loop actually, where scholars would go through the transcription and then maybe manually correct things?
And this would
be a great signal for your system.
Critical for us. Critical. It is not our goal to produce things and hope that they are useful. It is our goal to ask people what they want, produce things, talk to them about it, see what they want to do with it, and absolutely do that. So things like finding replacement things. We talk to people who work on Nahuatl text to find out what are the things that we should be expecting. What are the things that we need to build our system to be able to handle. So definitely that's a thing that we always want to keep in mind.
And even after all this is done, right? After we produce transcriptions that are being used by scholars, right?
Mm-hmm.
I mean, there is at least a potential that they would manually correct the text, right?
Yes.
Which is a supervision signal that.
Yeah. So one of the issues that we came across early on, and is still kind of plaguing us, is that there's not a lot of Nahuatl text. There just isn't. And so this thing is actually really useful for us because we can produce more Nahuatl text. And it's not going to be perhaps great, but we can give that to people and they can correct it, which then becomes language model training data. And so that's definitely a thing that we are trying to do. Yeah.
So how do you distinguish between like code switching versus borrowed words versus like proper nouns and?
We don't distinguish. I mean, borrowed words, we're calling code switching. I mean, the phrase code switching is not technically correct to encompass all of these things because there's mixed language use and borrowed words. But if we come across a borrowed word in, for instance, Nahuatl, which is extremely common because there are words that they just adopted, we would manually, or the system would label those as being Spanish or Latin.
So in this collection of books, is the vast majority of them like intended for a monolingual audience, or?
I mean, not necessarily, right? So a lot of these books, a lot of these books are religious in nature, and so they were written by monks for monks, and so they contain things like Spanish text, but they also contain religious writing that's in Latin. So it would be expected that somebody would have to be able to read Latin, or the books that are written about Nahuatl or in Nahuatl. We would also have to have Nahuatl speakers, whether they be the Aztec population or people who had learned Nahuatl later. Yeah.
I apologize if you already mentioned this, but how do you determine what the normalized form is? It makes sense, like the original form is just what is there on the page, but how do you determine?
Yeah, so that's a great thing about the unsupervised case is we can produce whatever you want, where what you want is characterized as what the language model training data comes in as. And so if you want, for instance, for the Spanish case, right, you can feed in modern Spanish and it'll produce something that's more modern, or you can take books that are hundreds of years old. You can feed in Don Quixote and it will produce something that's slightly different. And then with the Nahuatl case, you can give it an older orthography, or as people produce new orthographic conventions, you can feed in new stuff and it will be able to keep up to date with the ways that people want to transcribe things. Yeah.
So what was the language model you ended up using? Because you mentioned the 6-gram character model. Did you just stick with that?
So we used the code switching model. So we had 3 6-gram character models that were wrapped in together and able to switch between. Yeah. So yeah, the 6-gram model worked pretty well. We haven't messed with trying to change the 6, but you could imagine that with Nahuatl, because we have less data, but those are things that we haven't tuned. All right, thank you.
So good afternoon. My name is Lucy Vanderwendy, and so I am the Microsoft representative for this part of the talk. We always have one presentation from UW and one from MSR, but I'm kind of, I sit on both sides of the lake. So I'm going to introduce Maliha Yatiskan to you. My colleague, she and I started a project several years ago, which was funded by MSR Outreach. And so as a result, I've now also become faculty at UW. So I don't know quite which way I am. So Maliha is a wonderful colleague. We've had the pleasure of working together the last couple of years. She got her PhD at University of Washington, did a postdoc there, did some work in industry at Siemens, so kind of also sits on both sides of kind of the fence there, and now is associate professor in the Department of Biomedical Informatics and Medical Information or Education at the University of Washington, and she leads the UW-BioNLP group, which is, we enjoy talking with each other, and we should get to share a lot of information about this space. So pleased to introduce Maliha to you.
Thank you, Lucy, for the interaction. So today, the title of my talk is Extracting Semantics from Clinical Text. And today I'll be talking primarily about our ongoing research at our UW-BioNLP lab. So all the content that we will present today is available at this website, all the papers, tools, and hopefully we'll release some data sets soon. So what we do in our lab is we do process electronic medical records. EMRs capture the healthcare from various perspectives. So it contains structured data about patients that involve problem lists, lab results, pharmacy orders, discharge diagnosis, and many, many other parameters. And also, it contains a vast amount of unstructured data in the form of free text. So some examples would be radiology notes, op reports, admit notes, discharge summaries. So they all describe the story of a patient during their hospital visit. And in our institution, more than 80% of patient data is actually in the form of free text. So this represents us really good opportunities to formulate NLP problems and work on them. So this is an example discharge summary. This is coming from a publicly available data set, so it's okay for me to share with you. So as you can see, it represents many of the aspects of the hospital course from multiple different dimensions. But because this is free text, if we capture this information in the form of only keywords, we would get some knowledge out of that, such as like, most probably this person might be suffering from acute leukemia or maybe having problems with headache, nausea, vomiting, diarrhea, and maybe has some history of like colon cancer, perhaps, depending on location of the document. But if we add like section information on the top of that, we would know that acute leukemia is actually related to the present illness and colon cancer is related to somebody in the family. So if we add more information on the top of that, for example, temporal information, we can build a timeline. Negation is very, very critical in our research because most of the symptoms that are critical for diagnosis is like presented as absent if the clinicians do not observe them. So there are so many negation mentions in clinical records. For example, when we add negation, we would know that this patient is not suffering from headache, nausea, vomiting, or diarrhea actually. So it's quite important for us. And also another piece of important information is uncertainty, where clinician cannot decide whether a given symptom is present or absent, but like questionable or like hypothetical or conditional or something like that. So on the top of that, there are other layers of information, of course, reported in these texts. For example, medical tests are interesting to be able to extract. With medical tests, I mean that like the test itself and the value outcome of the test. Also, medical treatments applied to the patient during their course of visit. So our research interest in our lab is to make information hidden in vast amounts of clinical data, mainly in EMRs, more accessible to improve clinical research and patient care. So we are after not the EMR design, but the secondary use of EMR data. So these are some clinical applications that we are working on actually. When we think about like formulating a problem that revolves around EMRs, we look at usually the problem at different levels. So one level would be the note level, right? You have a given note and you can extract all medications, treatments, tests, findings reported in that report. And one example application would be is billing, not that interesting for us, but we are more interested in the quality improvement part. So we have an ongoing project right now that involves like processing radiology notes for extracting incidental findings. And from incidental findings, we mean that you go to see a radiologist for a particular test, for example, like totally like perhaps a checkup, and then they see something very irrelevant to the purpose of the test, such as like a lung nodule or something. And then they would put a follow-up information there, like saying that like this is suspicious, it needs to be followed up in a certain number of months. And if this information is not well communicated to the referring clinician, then bad patient outcomes like unfortunately happens, and it's a real problem. So NIH funded our project. So this is one project we have at the note level. We only look at patients at the notes levels for this one. At the patient level, there are multiple questions we can ask. One question we are very interested in is to be able to answer, does a patient have a given disease based on a bundle of data? For example, this may be their whole hospital visit, their whole ICU stay, or like things like that. So mainly we try to answer the question by looking at all the accumulated data for that patient. And this is for disease surveillance, and I'll be talking more about this ongoing project predicting the onset of ventilator-associated pneumonia, so I will not talk more about that now. And the last level is the population level, where you look at the EMR as a whole, and you try to extract a group of patients that like mainly meet certain characteristics for different purposes. This may be for cohort selection, for clinical research, or for outcomes research. We have two ongoing projects right now related to that, and one of them is predicting liver cancer stages for mainly like for treatment outcomes, such as like if you can predict the liver cancer stage, it goes from I think 1 to 5 or something. I always forget about that, 1 to 4 or 1 to 5. So if you can map that, like the patients to that stages, and you know what kind of treatments apply to those patients, then you can estimate what would happen if another patient would come with similar characteristics. So this is for outcomes research at the patient level, and a new project which we recently initiated is extracting environmental and social factors for disease outcomes. And I'll be talking more about this project too. So for all these kind of like projects, we have to look at,
So if a patient comes back multiple times, will each of those generate a different free text field, or will it just be one big long record?
So every time like a report is generated, it's a separate report. It doesn't bundle up. Yeah. So to answer these questions, it's quite important for us to be able to extract the structure and the semantics from these free text notes. And we have done some research on this prior for our previous projects or ongoing projects, and we released some tools. One of them is a statistical section chunker, which for a given clinical note, it will identify the boundaries of the sections, and then for each section, it would map it to a section header. And another tool we released, and it's very popular actually, is the assertion analyzer, where we have a sentence and a medical concept, and it will tell us whether it's a present, absent, conditional, hypothetical, possible, or not patient. So these two tools we released, and we are currently working on an event extractor, and also a co-reference analyzer. The co-reference analyzer, I will be talking about the event part, but for co-reference analyzer, we are interested in co-reference extraction for tumor information in the radiology notes. So it's very, very interesting because like this captured like tumor information, apparently very important for us to extract for the tumor cancer stages, because the number of tumors, like where they are located, and there are mentions everywhere. So we are building that, and we are releasing that hopefully mid-summer. So in the remaining of the talk, I'll be talking about two clinical applications. Mainly, I'll be providing some information, but will not go very into detail of the technical details. I will be happy to talk with you after the talk if you have any questions about that. So the first application is phenotype modeling in the ICU. This is joint work with Lucy, Faye, and we have two clinical collaborators, Mark Werfel and Heather Evans from UW-Madison. We had a bunch of postdoc and students worked on this project. And our motivation is to develop an automated screening tool that would accurately identify critical illness phenotypes in the ICU. In this context, I use the phenotype as a disease name, and our disease is ventilator-associated pneumonia. We picked this disease because this has been the most deadly disease in the hospital-acquired infections. So, and it's kind of quite interesting because it's a consensus definition, it's consensus diagnosis, so some information will come from pretext, some information will come from structured data, so it's perfect like prediction problem for us. So for this project, we created a really nice data set which included all free text notes generated during the patient's ICU stay from admit to discharge. And we had all the structured data that is related to our cause for ventilator-associated pneumonia. So we capture vital signs, all the patient-related information, but also we captured ventilator bundle elements because this infection happens because these patients are intubated to ventilators. So the angle of the bed or like what kind of respiratory treatment is given also being captured here. Before doing the annotation, we of course looked at the what like clinicians think a VAP patient. And as I mentioned, this is a consensus diagnosis, like the first piece coming from radiology notes, mainly talking about this like lung problems. And the second piece talks about like fever and other problems that is captured in the structured data. And the last one is coming from the microbiology results. So mainly it's a semi-structured text. Currently it's captured in structured format, but at the time we built this data set, the text was like the report is a text blob. So we had to do something about that. For annotations, we had a clinical collaborator and we created a almost 800 patient data set where 123 were then positive for VAP. We captured more than 14,000 ICU days. These patients, some of them are really sick because they stayed like 163 days in the ICU, which is crazy long to me. And we captured more than 27,000 free text notes. And we looked at different scenarios in this project because this is a really interesting data set, so we explored some options. In the first scenario, the task is to decide whether the patient had a specific phenotype. So we looked at the data retrospectively. We bundled all the data and determined which ones are positive or negative for the given disease. And this was for clinical research and cohort selection purposes. One of our clinical collaborators was a geneticist, and he wanted to create cohorts of patients, so we did the study for that purpose. The second scenario is the Has phenotype one, where for a given point of time, you try to decide whether the patient has the disease or not, and this is for phenotype surveillance for the hospital case. And the third one is will have phenotype, where you are at the timestamp t and you try to predict the future whether the patient is a high risk or not. And this is for clinical decision support. So for the Had phenotype one, we built a very basic baseline. We used unigrams, and then we used some clinical terms. We didn't use structured data in this one because because when you bundle all the data together, like usually a mention of pneumonia happening in the pretext already. So our performance when we did the baseline in a very, very simple format, this was an SPM classifier, it was 50%. When we added like section information and assertion information, negation and everything, our performance went up to 85%. So it really mattered. So for document classification tasks, usually you don't need to add more context to n-grams, but in this context, it really helps to improve the performance. So we did some error analysis, and we realized that it's not good to add microbiology notes as n-grams because, as you can see, you cannot get much out of this when you represent this kind of weird text with n-grams. So we built an information extraction tool that would capture these components of these test results in a more structured way. So we did that. It's a very, very basic like information extraction task, so I won't go into details of it. For the second part, we realized that assertion classes were not powerful enough for most times. For example, we are trying to capture present, absent, conditional, hypothetical, possible, not associated with the patient. But if you have the second example, the report 2, like it says gradual improvement of this very, very important indicator of pneumonia. And when you run assertion classifier on the top of it, it will say present. So we had to do something about that. So this is our ongoing research. One of our students working on mainly extracting clinical events with change of state information. So this example is coming from real data actually, where 3 ICU days, same patient, 5 reports. And this is the event, diffuse lung opacity is consistent with pulmonary edema. And it says like no change worsened, no change gradual improvement. And the task is to be able to capture that like event and its current like changing correspond to the previous reports. So to be able to do that, we built an event description, of course. We capture these like radiological events from anatomical measurement, value, and change of state, and also link to the previous report kind of attributes. So we capture these pieces of information for each event. And we created a corpus mainly composed of more than 1,000 sentences. We annotated them for this event definition. And these are some example annotations. So in the first one, as you can see, we have this like radiological event like captured with all pieces of information that we defined. And in the second one, we have 2 events actually that have shared entities. So this was the extraction task. And we also enhanced that with coordination and negation after doing some initial analysis of the corpus. So in terms of performance, like we built a name entry recognizer, of course, to be able to extract the pieces of highlighted text. And these results are coming from Stanford NER package. We had to define some domain-specific features, of course, but our performance is currently quite good for entity extraction. And we use the mult parser to be able to extract the links, and our current performance is at this level. So this is one piece of that's ongoing research. Our student is working on this right now. But like if I return back to our like phenotype extraction task, so we are doing research currently also on the will have phenotype scenario. And the task is like to be able to predict VAP in the next 8 hours based on data collected 24 hours prior. So what we did for us is one of our new students is working on this project where we use only structured data to be able to extract, like to do this prediction as the baseline. And we mainly trained a Bayesian network by using a Microsoft tool, WinMine. And our current performance is at this level, the baseline performance. And of course, the next steps will be is like, because this is a consensus diagnosis, we are going to add text features coming from reports. We will most probably through first like n-grams, and then we are going to through like these event features and also the micro features. Okay, so I'm going to move on to the second clinical application. In the second clinical application, what I'm going to talk about is like extracting, very different from the first one. This is about extracting lifestyle and environmental factors from clinical records. So this is the population level one. This is joint work with Lucy, as well as like a new faculty in our department, David Croston, who is a biostatistician. And here the motivation is lifestyle and environmental factors play a significant role on our health actually, and they are very well recorded in our clinical records. However, when people do like disease outcomes research, they usually focus on like genotype-phenotype extraction type of tasks without taking the environmental factors out of the equation, although most of the time genome stuff is like kicked in because you add something from the outside. So in clinical care, like 5 to 10% of cancers are attributed to hereditary factors, and while 90 to 95% have been found correlated with these elements. So we thought that like it would be really interesting to look at the clinical records to observe how these elements are represented. We looked at UW data, we looked at some existing literature on the topic, and we found out that like the doctors actually like put a really good effort to record these elements. Like they report, like when they ask you questions about your daily life, actually they are writing really serious details like that you are not aware of. So the purpose of this project is to be able to automatically identify those elements and then do some sort of like outcomes research at the population level. So what we did was like we looked at, of course, some existing literature, also the EMRs, and we came up with this list that we thought would be interesting to look at. Also, we had some guidance from some clinicians while we formulated this list. And we defined these factors with many attributes. So what we are after is not to know that whether a person is a smoker or not, but we want to know that how much smoking the person is like experiencing, or like if they quit smoking, how much like they smoked in the past, so that we would have a gauge of like quantify mainly the exposure amount. So we mainly define these attributes to capture all the possible details represented here in the clinical text. And we created a data set. Mainly we mined from a publicly available website, MT Samples, which is medical transcription samples website. We picked history and physical notes because they are very rich in social history definitions. And then we had an annotator, a medical student who agreed to do the annotation for us. And we did double annotation, a small set, and we then mainly annotated the whole data set. And these are some annotations examples. As you can see, these are coming from the publicly available data set. However, we compared this with our own data set at University of Washington to see whether this publicly available data set is like a good representation of whatever really represented in a clinical environment. And we agreed that it's very similar. And the reason why we decided to annotate first the publicly available data set is then we can release the data set, because otherwise we cannot do anything with it. So this is an annotation example across various factors. These are some statistics about the annotation. Of course, substance abuse has been annotated more frequently than the other factors. And it's also partially because of the size of the current data set. It's a very small data set. So we decided to start from substance abuse extraction first. And then these are the attribute statistics. So the ongoing work is we are in the process of building the extractors, and I do use this data set as part of the clinical NLP class. I do teach at the University of Washington right now, so some of you are actually working on this data set. So after we built the extractors, we are going to apply this to the UW Medicine Clinical Repository for disease outcomes research, of course. And then another aim would be to apply this to another project which is called eMERGE. Actually, this is a really cool project which involves 10 institutions across the United States, and they do mainly genome-phenome analysis work. So if we can add environmental factors as a parameter to this equation, it will be really interesting research. So I would like to acknowledge my collaborators. I want to acknowledge, of course, my lab. I I'm very privileged to work with Lucy, Faye, and many of our students. So, and also we have many clinical collaborators. I just listed people who do research, who did something about this project. So, and questions? Yes.
In existing, so some of the work that we've been looking at where people are doing like large-scale hospital record, trying to predict something like heart failure readmission.
Yeah.
What is typical practice? Do they just do a keyword approach? Are they just doing the first thing you said, like where they're not paying any attention to negation or anything like that and just chopping up all the words and throwing it in, or are they doing something more sophisticated and typical?
So it depends on who is doing it, right? So it's kind of sometimes, I don't know, you are asking a very wide question. Some people just do actually regular expression searches, like they would have a certain phenotype or disease names like in their minds, and they would do regular expression searches. They would add negation on the top of it, perhaps. Like if the phenotype is very clearly written in the text, like people's preference would be that first. And if it's not that clearly written in the text, and you would need to add more information from the rest of the like reports or other information such as medications, they can go with building like classifiers, like based on the whole data. Yeah, so it's all over the spectrum actually, and it all depends on your disease type. For our disease, you definitely cannot get the will have type of prediction by only looking at the text or by only looking at the structured data. So we decided to combine them both. So. Yes.
One question. I would like to ask about the annotation tool you are using to label the training data.
Oh, we use Brad.
Brad.
Brad from University of Manchester. Yes. So it's quite a cool tool actually. It's very easy to set up, and depending on, of course, it depends on the type of annotation you want to do. It doesn't let you to do everything, but it's pretty sleek actually. So it's.
Okay.
Yeah.
Thank you.
The only thing that it does not do is between documents.
Oh yeah, it doesn't do
links between documents, but you can link any sentence within the one document.
Okay, thank you.
Another question. Okay.
Maybe another question about the evaluation when you compare the ground truth to the extracted entity. Is it exact matching or soft matching?
So that one is exact matching. Like,
if you miss one word, you consider it false.
Yeah. But like, just a sec. I need to double check the table. We do calculate both actually. We do calculate, this must be a token level. So it's not, it's inexact. It's, yeah.
Okay.
Yeah. Because like, if I don't, you can correct me, because like this should be inexact match, right?
No,
Token
this
match.
is actually exact match.
Oh really?
But
Okay.
you actually have word level match, but all the kind of span level match is exact match.
Okay.
Do you differentiate between getting the beginning or the continuation of the entity?
So for this one, like as Faye said, it's strict that it's strict,
Exact.
but like exact. But like for token match, I don't think we do. It's like mainly we calculate at the token level, like everything, and then like if there is a like gap between them, it will still get a credit. Yes.
This may be a little bit of a crazy question, but it goes into politics actually, because I mean, you know, this is the kind of research that obviously it could have an incredible positive impact on people's lives, right? What's the level of like national coordination of these things, or the level of support or the awareness amongst, you know, funding agencies, the importance of that? And what would be sort of your top wish list, you know, if you could make the policies and you could?
So I think it depends on the application. For example, there is an agency under NIH called AHRQ, which is about improving the quality of healthcare, who funded our radiology work actually. So for that one, they are about that. So they are mainly try to decrease the number of mistakes made during the hospitalization and things like that. But like it's for that one, it's like for those kind of projects, it's easier to get funding. But phenotyping projects, if it has direct impact on the patient, it's harder to get funding. They usually claim that it would be, how can I say, it would be a little hard to implement in the real case, like real hospital case, although it's kind of, the project has been initiated by a clinician actually, so our clinical collaborators came to us with the need that like we would like to have a predictor system that would tell us who are in like high risk for this phenotype. But from funding point of view, it's harder to get funding for that one than other one, the radiology project, where we try to identify the incidental findings and things like that. Because that highlights, that project is about like highlighting the report. The other one has direct impact on the patient care. So I think the worries are more on one side. Yeah. And I would be more happy, of course, if we can get more funding of this kind of research.
And is it coordinated at a national level? So let's say, the UW with Microsoft is working on, some of the specific problems, and then another place is becoming the center for working on, other phenotypes or other problems. Or is it basically just wherever the research bubbles up, that's where some funding goes, and the best ones sort of shake out in the end?
I think the NIH funding way is a little bit different than NSF's one. Like they tend to fund bigger projects more. So if a project involves multiple institutions, you get more chance, for example, to get funding for a phenotyping project. For example, eMERGE is a really good example for that. It's a really, really big project that involves like 10 institutions. It's crazy big. But what they are all doing is like they mainly like extract phenotype information from EHRs, and they also like collect the genome information from patients, and they do genome-phenome-wide analysis of these things. So I don't know, like it's a mix, I think. Like it's sometimes, of course, like some institution would be more powerful in terms of in certain areas, and then they may just draw more funding. NIH, I think, tend to like give bigger amounts of money that would involve like lots of institutions, and it's understandable, I guess, because then perhaps it will have more impact.
If I can add, you also know that research kind of is drawn to wherever there's data, right? So I2B2 has made some small, medium-sized data sets available. So there are a number of institutions across the US and worldwide who do smoking cessation detection, do obesity detection, and so on. But that's just where the data is. And the real problem with working in this space is the creation of data, because the hospitals don't have this data. And there is a huge concern for privacy with, kind of working on EMRs. So it's a challenge.
That's why we try to annotate publicly available data so that we can make baselines more available. But thank you.